Hello and welcome to the MR-CFD. The present problem simulates two-phase mixing by mixing tank by ANSYS Fluent solver. A mixing tank typically consists of a cylindrical vessel and one or more impellers. The impellers are driven by an external motor that rotates them. When the impellers rotate, they create a flow of fluid in the tank. This flow can be axial, up and down, or radial, outwards towards the wall of the tank, depending on the type of impeller used. The fluid flow causes the substances in the tank to move and collide with each other, leading to their mixing. The closed mixing tank contains water liquid, while the impeller starts rotating with 120 revolutions per minute angular velocity, creating a massive vortex in the middle of the tank. The geometry of the present model is three-dimensional and has been designed using ANSYS SpaceClaim software. We do the meshing of the present model with ANSYS meshing software. The mesh type is unstructured, and the element number is about 1,260,000. Around the shaft and impeller, a boundary layer mesh with 5 layers is applied so that Y+ does not get too high in these sensitive areas. Also, according to the figure, the impeller is located in a separate zone called the MRF zone, where the rotational motion of the impeller within this area will be defined later. First, we need to import the mesh file to the ANSYS Fluent software. From File tab, Read, and then click on the Mesh button. Then select your mesh file to import it in the software. We can show the geometry by clicking on the Display button, though we can select every surface to show in the display window. All right, let's start the simulation process. At first, we have to consider some general assumption related to the simulation solver, which are as follows. We use pressure-based solver type because we are dealing with an incompressible fluid, which is water. A transient solver type is used in this simulation to capture the dynamic behavior of the mixing process over time, ensuring accurate representation of particle-fluid interactions, turbulence, and time-dependent flow characteristics. This approach is essential for understanding transient phenomena like mixing efficiency and particle distribution in the tank. Also, we want to consider the gravitational effects in our problem, so we define 9 as 9.81 meters per second squared in y direction. We get to the materials section. To enter water and iron powder as solid particles, we click on Create Edit button. Then from Fluent Database, drop down the list and select Water Liquid. In Multiphase section, we select Eulerian multiphase model with implicit formulation to simulate the behavior of iron powder interacting with the fluid phase. Then in the Phases section, we have to define these two phases. Next, go to the cell zone conditions. We have two zones, a zone within which the impeller is located and is rotating, and a zone around the rotating zone that includes other parts of the tank and does not contain rotating components, such as the impeller. Now we get to the solution part of the simulation. We use the phase-coupled simple algorithm for pressure-velocity coupling. It is an extension of the simple algorithm for multiphase flows. It solves momentum equations for each phase separately, then couples them through interphase drag terms. Since the main purpose of the issue is to investigate water movement inside a mixing tank, its related contours can be shown in the figures. Two-dimensional contours related to pressure, velocity, and wall Y+ were obtained. In the case of pressure, it is visible that the amount of water pressure in front of the impeller is much more than the amount behind it. Here you can see the water axial and radial velocity contours from above and the water velocity magnitude from front. As was expected, the speed of the flow behind the impeller is more than in other areas in the domain. The next contour is the Y+ contour for the water phase on the shaft and impeller. This contour will be approximately the same values for the iron powder phase. As is clear, the Y+ value of the rotating components, which are shaft and impeller, is approximately in the range of 0 to 7.3. So using enhanced wall treatment for this simulation is correct because this range falls within the viscous sublayer and buffer layer regions, which is Y plus bellow 11.225, where enhanced wall treatment model performs optimally. The radial velocity of water versus position on a line along the y-axis near the impeller is shown here. As can be seen from the graph, the maximum radial velocity of the water occurs approximately halfway through the impeller blade and is about 0.048 meter per second. It should be noted that the negative values of the velocity in this graph indicate the direction of the radial velocity vector, meaning that at those locations, the radial velocity vector is pointing toward the center of the impeller, not outwards. The moment on the impeller versus time graph is shown in this figure. We see that the moment on the impeller increases significantly up to about 0.0215 Newton meter in the initial moments of the solution, up to about 0.08 seconds. After that, until about 1.7 seconds, the moment on the impeller decreases and again takes a constant value of 0.002 Newton meter. This initial jump in moment is because the impeller starts rotating from rest. Finally, you can see animations of water velocity, magnitude, and iron powder volume fraction at different time steps.
To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.